So hello everybody and welcome to today's AATRN seminar. Today's speaker is Steve Oudot and he will talk to us about estimating the persistent homology of Rn values functions using functional geometric multifiltrations. Please take it away.
All right, thank you very much for the introduction, and I want to thank the organizers of the seminar for inviting me. I really appreciate it. The work I'm going to present started out as a master's project with a master's student, so Ethan André from École Normale Supérieure, and then it grew to become like part of one of my PhD students' PhD project, so Jean Levy. And recently, at the beginning of this year, David Loiseau joined our group as a postdoc, and so he has joined the project as well. And you will see that the statistical part actually has a lot of that is coming from him. So the project is about estimating the persistent homology of Rn-valued functions using functional geometric multifiltration. So that's a lot of words. I'll start by explaining the last few words, and then I'll go to the main question, which is phrased at the beginning of the title. So let me talk about functional geometric multifiltrations, so what I call functional geometric multifiltrations, and perhaps the archetypal example of this is the function groups multifiltration. So what is the function groups multifiltration? So the setup is that you have a compact metric space, let's call it X, and you have a function f on X that is valued in Rn. So the slide says Rd, but D should be understood as being n here. And then what we do is for a given scale parameter delta, you can build a Rips complex of that space of parameter delta. So here's a picture. So I have my function here that goes from X to Rn. And then here, for a certain parameter delta, I'm building the Rips complex of parameter delta over the space. And then what I can do is I can, of course, if I vary delta, I will get a one parameter family of Rips complexes. But what I can also do is, for instance, a fixed delta, I can actually filter the Rips complex by the sublevel sets of the function. Okay, so I get this way. What I get is a n plus one dimensional multifiltration, where the first parameter is the scale parameter and the Rips parameter, if you want. And the rest of the parameters are the ones given by the filtration, the sublevel sets of the function. Okay, so that's what we call the function Rips multifiltration. So it has been considered like in the past, like on multiple occasions, and maybe the most well-known version of it is what we call the density Rips, where basically F is a codensity estimator, and you're filtering this codensity estimator by its sublevel set. And actually, this version of the function Rips multifiltration was proposed as early as the first paper in TDA about multiparameter persistence back in 2009. And so since there have been many variants that have been considered, so the function Chesh, where you replace the Rips complex or Rips filtration by a Chesh filtration, and of course, there is the special case of the density Chesh, where the function is a codensity estimator. Then there's the degree Rips, there's the kernel Rips, there's the subdivision Rips, etc., etc. And these multifiltrations have some interesting connections between one another. Some of them are nice approximations to the others, and so on and so forth. So far, they've been considered mostly through the lens of stability. Okay, so the main question that people were asking about these multifiltrations, besides how we can compute them and how we could compute their persistent homology, but beside this computational aspect, the main question that people were asking about this multifiltration was their stability. So what I mean by this is that if I perturb my space, if I perturb my function, I'm gonna get another multifiltration, and is it possible to relate the two multifiltrations? Okay, so there has been a whole series of stability results that have come out. So here are a few examples of those. So there is one about the multi-cover variant of the multifiltration, where the stability is expressed in terms of the interleaving distance. And of course, there's a couple more examples that are listed here, and there are more for a few more again in the literature. So this is all nice, but I want to take a different viewpoint on these multifiltrations. I want to basically ask myself, what happens if my, if for starting from my compact set, now I take a sample, okay, a point sample from that compact set, and now I build the multifiltration on that point sample, and I want to know, I want to study that object as an estimator, okay? And of course, if you want to study that object as a statistical estimator, you have to ask yourself what would be the target. And if you look at these stability theorems or stability results, a natural target for this estimator would be the corresponding function geometric multifiltration or function roots multifiltration, let's say, built on the compact space itself. But the problem is, if you go to, if you discuss with a biologist or a physicist and you tell them, oh, I have this very nice estimator that's for which I have some convergence guarantees to its target, which is naturally the function Rips multifiltration of the domain, they will look at you and ask, what is this useful for me for, right? So instead, what they usually are interested in is X itself, not a Rips complex of X, not a Rips filtration of X. It's X that interests them. And in the case where X is filtered by a function F, they're interested in the pair X. And so that's why we decided in this work to change our target to be XF. And since we want to look at things from the persistent homology viewpoint, our target is actually the persistent homology of F. So what I mean by this is just the persistence module induced in homology or a fixed degree, say, from the sublevel sets of the function. So that will be my target. So what I want to do is to be able to relate a function geometric multifiltration based computing on P, a point cloud, a point sample. I want to relate this to the persistent homology of the function, of a function that is on the defined on the underlying space of the point cloud. So this viewpoint is not novel. It was actually considered already in the early years 2010, and there are two examples that I want to mention here, where like such convergence guarantees as the ones we're aiming for were described. So one of them is Tomato, which is a clustering algorithm, where basically what we were doing in that work was to say so the function was a density function, okay, or a co-density function, and what we were doing is we were building the density Rips, okay, so the function Rips filtration by filtration, with the function being the density. And we were studying the convergence of vertical slices in that density Rips. So what I mean by this is that, you have these n+1 parameters, and where the first parameter would be the scale parameter, and we would basically fix a scale and filter a single Rips complex and look at how well this restriction would approximate the persistence model, the persistent homology of the density function. And then there was another contribution more recently by Alexander Roller and Luz Kokkola, which is another clustering algorithm, which is called Persistable, where they were using a different bifiltration. It was not the density Rips, it was the degree Rips. And they were not taking vertical slices, but they were taking diagonal slices or leaning slices, which at the limit, as the number of points would go to infinity, that leaning slice would actually straighten up until it would converge to the like a vertical slice aligned with the vertical axis. So in this work, we're trying to generalize both these contributions, so both Tomato and Persistable, in two different ways. So the first way is that we're not going to stick to density functions. We want to be able to consider more general functions than just density estimators. And the second way we generalize that line of work is that we want to be able to consider functions that are valued in Rn, not just in R. Okay. And so what we aim for is to provide a framework to analyze these multifiltrations as estimators. So we want to be able to basically to show the convergence of statistical estimators to get deviation bounds, maybe some confidence intervals, and so on. Okay, so here is the problem as we phrase it. So the setting is that we have a compact metric space. So we're going to put a metric on our compact space because we want to build Rips complexes on it. And we're going to consider a real valued function, an Rn valued function on X. So the function is F, the space is X, and both of them are unknown. Okay, so we do not have access to either of them. What we do have access to is a finite sampling of X. So I'm not making any statistical assumption for now. I'm taking a viewpoint of geometric approximation, where basically I'm going to take a subset, a finite subset of my space, and I'm going to make some deterministic assumptions on it. And then I will say that under these assumptions, I can say this and that on my approximation, and then we'll derive some statistical results from that. So for now, I have a finite sampling P, a finite set of points P. And what I know is the values of the function at the points of P and the pairwise distances between the points of P. So by pairwise distances, I mean the distances in X. Okay? And my goal is to estimate to approximate, probably in the interleaving distance, because that's the distance I will be interested in. So I will try to approximate in the interleaving distance the persistent homology of S, that is, the homology of the persistent homology of the filtration of the sublevel sets of F. So here's a little picture of what's going on. So this is, I have a function that is from R2 to, the unit square in R2 to R. Here is its graph. And my unit square is actually sampled. So I have this set of points here, that's my P. And what I have access to is the pairwise distances between the points and the function values at the point. So the function values are color-coded, with orange being higher values and blue being lower values. So this problem, as it is phrased here, was considered actually in 2009 in a paper that we published at the time, which considered the case of functions that are valued in R. So n was equal to 1 at the time. And so I can basically explain what we were doing at the time, because we're going to do exactly the same thing. And the lesson that we learned from this project is that sometimes it's good to revisit old papers, because it happens so that some of the ideas actually work in higher dimensions. It's rarely the case, but in this particular case, it did work. Okay, so just a remark. So we don't have full access to the domain. We don't have access to a triangulation of the domain, for instance. We only have access to a point sample. So a good idea is to try to use a proxy for the domain. And the proxy we're going to use is, as you would imagine, is going to be a union of both. Okay? So I'm going to take a union of both centered at my data points. Okay? And I'm going to try to approximate the sublevel sets of the function by unions of goals centered at the data points, but not all the data points, only the ones that live in the sublevel sets in question. And so in order to get some interleaving, I will have to make an assumption both on the sampling density. So I want to, so the assumption I'm going to make from now on is that my sample lies at it lies in the space actually, and it's at Hausdorff distance at most epsilon for some constant epsilon. And I'm also going to make an assumption on the regularity of the function. So for simplicity in the talk, I will assume f is C Lipschitz for some unknown constant C. But in the paper, we actually look at omega functions that admit a modulus of continuity. So how does the interleaving with the sublevel sets work in this setting? So let me put up some notation. So first of all, given my function f, I'm going to call capital F sub t the T sublevel set of F. Okay, so it's the pre-image of this down set here. And now I'm going to call P sub T the trace of that sublevel set on my point cloud. Okay, so in this picture, the sublevel set Ft is in gray, and the trace on my point cloud is the set of points that are marked in black. The rest of the points marked in white are actually the data points that lie outside of the sublevel set. And now what I'm going to do as a proxy for the sublevel set is going to be the union of goals centered at the points of P sub t of radius delta, where delta will be a user-defined parameter so far. Okay, so I fix the delta and I consider the union of goals of radius delta around the points that live in the sublevel set. So here's in this example what this union of goals would look like. The goals are in dashed lines. And as you can see, the union of goals is not included in the sublevel set, and the sublevel set is not included in the union of goals in general. But it's not far from being the case. So in fact, there is an interleaving if I assume a function to be sufficiently regular. So here is C Lipschitz. If you assume the function to be C Lipschitz, then you have a C delta interleaving between the sublevel sets of the function and the filtration given by the unions of balls of fixed radius delta around the data points, where it's actually the point cloud itself that is filtered by the function values. And then I'm filtering the union of balls by adding one ball after the other when its center finally belongs to the sublevel set. Okay. So in the picture on the right-hand side, yes, do we have a question?
I was wondering, so you were saying epsilon is sort of the noise of P, right, with respect to X. Do you also have a look at the density of P? So like I know that usually one considers when you have a sample, you consider two parameters, like one is the density and one is the noise. Does this play a role here? Because you could also have P sort of, centered or clustered at one part of X, and that would not give you any information about the rest of the set. But I'm not sure if it's relevant in this case at all.
No, it is in two different ways. So the first way it is relevant is that F itself could be a density function.
Ah, okay.
And in the context of clustering, this is what people have been considering, like F be a density function. Actually, if you take F to be a density estimator, typically then you fall back to the setup of this tomato algorithm that I was mentioning earlier. But here F could be more general. And now as to your second, your remark that in fact all the points could be potentially centered, like sample around a hotspot. Actually, when we derive some statistical results, we're going to make some regularity assumptions on the underlying probability density, the probability distribution, and we're going to assume it typically to be AB standard, so that you avoid these clusters.
Okay, thank you.
Yeah, so you've got an interleaving here, and you can see it on the right-hand side, where basically if you shrink your sublevel set a bit, so if you take a sublevel set with a slightly smaller level, then you actually fall into the union of balls. And on the contrary, if you take a sublevel set with a slightly higher level, then you actually include the union of balls of the points around the points sitting in the original sublevel set F. Okay, and now the proof of this interleaving is very simple. It's just applying the triangle inequality. There is nothing in particular here, but it's a nice observation. So what this implies immediately is that you could use, as estimator to the persistent homology of the function, you could use the persistent homology of the filtration that I show here, which is again the filtration given by a fixed union of balls of fixed radius, and you filter that union of balls by the function values. Okay, so that means that the balls appear one after the other in the order given by the function values at their centers. Okay, but of course in practice, it's difficult to compute a union of balls, especially if you deal with general metric spaces. So a good idea to proceed forward from there would be to go from unions of balls to their nerve. Okay, so the idea here would be to replace the union of ball that you see on the right-hand side by its nerve complex, Chesh complex. And now if you take your delta to be within like a decent range, where the range would be smaller, at least delta would be smaller, strictly speaking, than the convexity radius of the space. So here I'm making an assumption, a regularity assumption on the space. So this is where I'm starting to put some regularity conditions on the space. If you assume your space to be a length space with, a geodesic space, typically, so the distance between any pair of points is realized by shortest paths. That's what it means to be a geodesic space. Then if this space has strictly positive convexity radius, that means that balls of radius small enough are going to be convex in a metric sense. And because they're convex, they're going to be contractible. And also their k-fold intersections will also be convex and therefore contractible. So you can apply the nerve lemma. Okay. So from the previous interleaving that we saw here, from the union of the balls filtered by the function values and the sublevel sets of the function, we get an interleaving at the homology level between the nerves of the homology of the nerves of the unions of balls and the sublevel sets of the function. Just because by the persistent version of the nerve lemma, the persistent homology of the filtered nerve complex is the same, is isomorphic to the persistent homology of the filtration by balls. Okay, again, please keep in mind that the radii of the ball is fixed here. Okay, so we're filtering by the function values. So already you're building one proxy for the space with the union of the balls, and then we're filtering that proxy by the function values. Okay, and now we just replace this union of balls by the nerve complex. So this is still not quite practical because building Čech complexes or nerve complexes is complicated in general. In some cases you can do it, but in general it's complicated. So I'm going to naturally move on from the Čech complex to the Rips complex, but then things become a little bit more complicated. So if you try to use the function Rips multifiltration as an estimator, so for instance, you build a single Rips complex of parameters delta that you fix, and then you filter it by the function values at its vertices. You take the lower star filtration of that complex by the function values. That I am not able to tell you if it is a good estimator or not. Okay? What I can tell you though is that if you take now a pair of Rips complexes, so I build two Rips complexes, one of parameter delta, which is fixed, and another one of parameter 2 delta, and then each one of them I filter by the function values. Then I have a canonical, I get two persistence modules in homology, but I also have inclusions between these two complexes. So these inclusions give me inclusions between the sublevel sets of the filtered Rips complexes. And therefore, in homology, I get a morphism between two persistence modules. And now my estimator is going to be the image of that morphism. Okay, so basically, I'm building two filtered Rips complexes, one included in the other, and then I'm taking the image of the morphism induced by the inclusion. And now the magic here is that if you take this as an estimator, then you have some approximation guarantees. So if you choose your parameter delta to be somewhere between a multiple of the Hausdorff distance between your point cloud and your space, and a fraction of the convexity radius of the space. So if you take delta anywhere in that range, then the interleaving distance between your target, which is the persistent homology of the function, and your estimator, which again is this image of the morphism induced in homology from a pair of two filtered Rips complexes, then this is bounded above by 2c delta. So this was proven by Fred, myself, and several other co-authors in 2009 for the case of functions that are valued in R. And what we did in this work was to actually, the proof did not generalize to higher numbers of parameters. So functions in Rn were not covered by that proof, but we actually re-expressed the proof in a purely diagrammatic setting, so a purely categorical way. And this way, the extension to higher numbers of parameters became natural. And so that's what we did, and so this is the new result. It's the same result as before, except that it holds for functions that are valued in Rn instead of functions valued just in R. So once you've got this result, then because you have a guarantee that your approximation is a good approximation in the interleaving distance, in practice you will not compute the persistence model, right? People don't compute persistence models in general. Usually they compute invariants, but now you can apply any stable invariant to your persistence module. And if you use a stable invariant in the invariant that is stable in the interleaving distance, so an example would be the fiber barcode, for instance, or the multigraded Banach numbers, which have a stability guarantee of a certain type, then you have immediately from this result and the stability of your invariant that if your target now is the invariant computed from the persistent homology of the function, and if your estimator is the invariant of that phi delta, then your estimator is going to be a good approximation to your target, where the approximation now will incurs a factor, an extra factor, which corresponds to the Lipschitz constant of the invariant seen as a function. Because the invariant being stable doesn't mean that the Lipschitz constant is 1, it could be more than 1. It could be less than 1 as well. Okay, so somehow what this result means morally is that this phi delta, if you see it as an estimator, it actually is a convergent, it's a consistent estimator. And we'll formalize this in just a few moments. So let me show you a few examples. So this example is taken from that paper from 2009. So this is the example that I showed at the beginning. And so here I'm going to approximate the persistent homology, actually the persistence barcode of the opposite of the function. Okay? Because then in H0, we see that this function has 6 peaks. And so in H0, in the approximating barcode, we see 6 long bars, and the rest is just noise that comes from both the noise in the function itself and the noise coming from the sampling. And then in H1, we see a long bar, which corresponds to this annulus here that appears in the supralevel set of the function, so in the sublevel set of the opposite of the function, and that persists for a while. So what you see on the right-hand side really is the approximation computed using the software that we had back in the days, which was using actually an algorithm by Edelsbrunner, Dmitry Morozov, and David Krensteiner. Maybe Yuri Mileko, I'm not sure, but anyway, they had an algorithm to compute barcode decompositions for images of morphisms between one parameter persistence models, which came out exactly at the same time. So these two papers were actually presented at the same conference, one after the other, so it was really nice. Okay, so here's another example coming from that paper. Still, so here we still have a function that is valued in R, but the domain is no longer two-dimensional. It's still two-dimensional, but it's no longer a piece of a Euclidean space. Now it's a torus, and I have the function that is whose values are color-coded here, where orange are higher values and blue are lower values. And here again, we see like the approximation on the left-hand side. Like what we see on the left-hand side is the approximation to the persistent homology of the opposite of the function. And so as you can see, we see four major main peaks, which are located here, 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 and here. And then we see, of course, 5 one cycles, because of course, each of these saddle points will create a cycle. And then there's the extra cycle coming from the tunnel of the torus. And then there's a 2 cycle that appears eventually to close the surface. And so here is just so you see, so these are immersions of the Rips complexes that we consider in this case. On a point cloud that we sample on the torus, and this is the smaller Rips complex, and this is the bigger Rips complex. So of course they don't live naturally in free space, but we immerse them so that we can visualize them. And the colors that you see are just the colors that you get at the vertices from the function values, which we linearly interpreted over each triangle. Now here's another example that was not in that paper, because that concerns a function that is valued in R2. So the space here is a circle. It's a very simple example so that we can see what is going on. So the space is a circle. And now I'm taking a uniform sample, like a set of points that have been sample IID according to the uniform measure on that circle. And what is the ground truth here? So I'm looking at homology in degree 1. Okay, so if I look, and what are the functions? What is the function? The function is just the coordinate functions in R2. So the first coordinate function is F1 here, the second coordinate function is F2, and now my function is just the concatenation of these two functions. It basically is the identity. So from the circle to R2. So now, what are the sublevel sets? Well, if I pick a point here, the sublevel set of that point is going to be this lower left quadrant. And so I should see in the circle, I should see nothing appear in H1 except once I've reached this point. Oops, sorry. Because then the sublevel set actually starts encompassing the entire circle. So at this particular point, I should start seeing some generators in H1. Okay, and it's actually a single generator, and that generator then lasts forever. So the ground truth here should be a projective, like a free module, indexed over R2 that starts at coordinates 1, 1. Okay, so I should have a free module that starts here at coordinate 1, 1. And now my approximation gives me a free module, as it turns out in this case. I also have a free module that starts not exactly at 1, 1, but not far away. And if I sample more and more points, basically this generator is going to get closer and closer to 1, 1. That's what our theorem says. So I'm going to skip this because I don't have much time. This is another example of a function that is valued in R3. This is an example taken from a paper by Oliver Weidman and co-authors from 2021. It's a data set that comes from immunohistochemistry. Yeah, there's naturally a function that is from R2 to R3 that comes into the picture in that example. And we show, well, we don't show the invariants because in 3 parameters, it's harder to really look at the persistence modules or their invariants. So what we show basically is the evolution of the interleaving distance between the ground truth, which is the persistent homology of that function, and our estimator. As you can see, as the number of points that we sample from the square goes to infinity, increase more. And as you can see, the distance basically decreases, and it seems to be like slowly but surely converging to 0. Okay, so if you look at this result, there are some loose ends here. So it raises actually many questions. And those are questions that were already raised back in 2009, and we didn't have the tools to answer them. So one of the obvious questions, of course, was to generalize to functions valued in Rn, but this is done. But now there are other questions. So first of all, this is an approximation result in the sense of approximation theory. It's not a statistical convergence result. So is there a way to build a statistical framework to get statistical convergence and possibly some convergence rates? And the answer is yes. I'm going to show you that next. Then there's the question of choosing delta, because delta is a parameter. And if you want to get statistical convergence, you will need to adapt your delta to the size of your sampling. And then, of course, there's the question that, here in this result, we're assuming that we're given exact function values at the data points and exact pairwise distances between the data points. Now, in practice, it's very rare to have exact function values. Usually those come from measurements or from estimations. And so they're rarely exact. And in the same way, it's likewise for the distances, the pairwise distance, because we need geodesic distances. We're treating the domain as an intrinsic space. So these usually are complicated they're not that complicated to estimate, but we don't have exact values, okay? And so we have a variant in the paper of the results. There's a variant of the result that actually deals with these noisy versions of the function or the pairwise distances. And then there's the question of computing the invariants. This is also in the paper. So you don't compute phi delta itself, but you want to compute some invariants on phi delta. And a good way to start to do that is to compute a presentation, like a free presentation of phi delta. And we explain how you do that. And from a free presentation, there's a whole collection of invariants that you can do. And then, at the end of the day, you might ask yourself the question, why are you using a pair of Rips complexes, right? Because I told you, well, with Rips complexes, I don't know how to do it with a single Rips complex, but I know how to do it with a pair of Rips complexes. So where does that come from? So that comes from an old paper. That comes from an old paper from 2008, where together with Fred Chazal, we showed that to infer the homology of a space, it was a good idea to use a pair of Rips complexes. But in the meantime, there has been a lot of development in following previous work by Jean-Claude Haussmann and Janko Flatchev on trying to understand the connection between the homotopy type of the Rips complex and the homotopy type of the underlying object, especially when the underlying object is a manifold. And it is true that if you put some sufficient regular conditions on the underlying space, you will be able to capture the homotopy type of the space with a single Rips complex. And but the question is, in our setting, because we're filtering the space by the sublevel sets of a function, it happens that the regularity of the sublevel sets will depend on the level that we consider. And especially near critical values, where we can expect that the sublevel set will become much more irregular unless we make some pretty stringent assumptions like Morse type function or Morse function, but otherwise we will have a lot of difficulty controlling what happens around the critical values. So I don't have a definitive answer about this, but I'll show you some experiments. All right, and I'll start with this one. So here's an experiment that we did. So on the right-hand side at the top, you see a point cloud in the plane. And these points are, most of them are sampled along 3 annuli, and then there's some scatter noise in the background, okay? And okay, so what I'm plugging here on the left-hand side is the value of the error between our estimator, so phi delta, and the ground truth. So the ground truth is the persistent homology of the height function on these 3 annuli. Okay, so I'm plotting the interleaving distance, if you want. Actually, it's the bottleneck distance because this is a function valued in R, so we're using the bottleneck distance. But you can think of this as being the interleaving distance between the ground truth and our estimator, and with respect to deltas, with the choice of delta. So what happens is that you see that the evolution of the error with delta is pretty erratic, and it basically starts at a pretty low value, but then it jumps up, And then it kind of has this U shape, which you would expect because there will be an intermediate regime, which is supposed to be the good regime for delta. If you look at this result, there is an intermediate regime, which is supposed to be the good one, where you have an approximation, a good approximation. And then when you leave the good regime, then again, the error might blow up again. But now at the bottom, if you look at the function, the phi delta, so I've smoothed the function grid by taking the image of one vertical slice into another one, as I described for defining phi delta, then here what you see is that the error now behaves in a much more tame way. And it does have like a very nice U shape. And in fact, it seems to be starting very high and then going very low. But in fact, this height is about the same as that one. Okay. So this is a much better approximation to the target than what just the function rips gives you, okay? Without the smoothing, without taking a pair of Rips complexes. Now, this still does not invalidate the hypothesis that maybe the function Rips filtration would give you a good approximation of the ground truth. Because, I mean, if you look at this curve precisely, you see that it's still bounded from above by basically a constant times delta. Okay? So I don't have a definitive answer, but in any case, smoothing, as it has always been observed to be, is a good way to get rid of much of the noise. Let me skip this. So this is an open question that we still have, which is to understand if we can replace our pair Rips complexes with a single Rips complex. Now I'm going to talk about the statistical framework. So how do you leverage this approximation result and turn it into a statistical convergence result? So for this, we're going to make some very standard assumptions. So we're going to assume that our sample points are sampled IID according to some measure mu, which is supported on X. So it's supposed to have full support. And so X is really the support of mu. X is compact. And we're going to assume that mu is sufficiently regular. So we're going to assume that it's AB standard, which means this. So this is a condition on the growth of the balls. Okay. And you can think of B as being the dimension, kind of an intrinsic notion of a dimension for the metric measure space in X. So now what we show is that if you know A and B, which is not the case in practice, but if you happen to know A and B, then you can select for each number of points K, you can select an optimal value for your parameter delta. Let's call it delta K. Okay, and that value is this. Doesn't matter what it is exactly, but it's basically log K over K to the power of 1 over B. And with this optimal choice of delta K, then you can show that at the limit, as the number of points goes to infinity, you're going to have convergence with high probability, and the expectation of the error that you're making for any C Lipschitz function is going to be bounded above by a quantity that is of the order of log K over K to the 1 over B. With a constant that is hidden here, which of course depends on basically on the regularity conditions that we put. So it depends on the convexity radius of the space. It depends on the modulus of continuity of the function, or the Lipschitz constant of the function, and it will depend on A and B. Okay. And meanwhile, you can also show that any estimator any reasonable estimator that you could build from your point cloud would have a convergence rate that would not, a convergence speed that would not be better than 1 over K to the power of 1 over B. Okay, so of course there is a gap between the two. Okay, so but it's not big. The gap is of the order of log K to the 1 over B. Okay, so up to log K factors, we've got an estimator that is minimax. And there are cases where people have proven in similar scenarios where people in TDA actually have proven that log K over K actually is the best convergence rate that you can get. For instance, when X is a convex set in Euclidean space. Okay. So what this result means is that basically what we used to use as a geometric estimation tool, this phi delta, now has become a statistical estimator, phi delta K, which converges at quasi-minimax rate. Delta K, if you know A and B, you can basically compute it. But if you don't know A and B, you can still estimate it. So you can build estimators based on subsampling techniques to estimate basically the Hausdorff distance between your input point cloud and the underlying space. This is a very standard problem. It's called support estimation. statistics, and you can estimate the house door distance, and from that estimation, you can set up your delta K properly. And you can also, I mean, what I wanted to mention is that this result, again, is phrased for functions that are C-Lipschitz, although this is not even recalled in the hypothesis, but again, in the paper, we consider functions that have a modulus of continuity, and then, of course, the modulus of continuity will influence the convergence rate. And so you could imagine that from here, you could basically use Bootstrap to try to get some confidence intervals and so on and so forth. We haven't done it yet, at least, but this is, you can definitely consider doing it. So here is an example of this result. So we took a Brownian motion where we sampled K points uniformly on the unit segment, okay, in R. And then, so we have these points that are uniformly sampled. And then when we go from one point to the next, we do a random walk, okay, vertically, we do a random walk. So we have these random walks here that we see. And basically, we want to use them from those random walks. We, from each of these random walks, we generate an estimation of the persistent homology of the Brownian motion. And then we take an average, and then we plot the average distance. We have the average error that we're making. And as you can see, as the number of points go to becomes higher and higher, the error decreases. So this is a log plot. And we see indeed that when we do a linear fit, we see that we get a line with slope 1/2. And why do we have 1/2? Well, because if we look at this result, we're in the case where let's see. So the underlying space is the unit segment on the real line, so it has dimension 1. But then, of course, so in principle, you could think of B as being 1. But why do we get 1/2 instead of 1? Well, just because the Brownian motion is that, well, the modulus of continuity is for the Brownian motion is not a linear function. It's actually square root of t, and this is 1/2 older, and so that's why we see the 1/2 appear here. Actually, so b is actually equal to 2, or no, it's actually equal to 1. But here you have a square root. Sorry, that comes from the modulus of continuity. Okay, so you get square root of log k over k, and so that's why you get this convergence rate, which is basically in half of which is well, on log scale, it gives you a line that that has slope 1/2. Okay. So I want to spend a couple of minutes to explain what happens in cases where the statistical framework fails, because in practice, I mean, the statistical framework is, to be honest, pretty stringent in practice because it's a very simple one. I hope that people will take over from here and, of course, propose some more elaborate and more general statistical frameworks in which our our results can be useful. But so far, this is all that we've done, okay? And so in practice, it's sometimes not the case that the points are simple IID, right? It's actually not so often the case, I should say. So even that would fail in many practical scenarios. So what do you do in that setting? Well, if you are a very good statistician, you could try to extend your statistical framework to your setting. But otherwise, what you can do is you can try to guess what the good delta would be, okay? How do you guess it? Well, the solution that we propose is to say we're going to do as people in TDA have always done, which is to not try to select a delta a priori. Just run the experiment with all the possible deltas at once, okay? Because that's exactly what persistent homology allows us to do usually. If you have one parameter persistence, you usually have a scale parameter, and then you run the whole thing with all the possible scales at the same time. And here we now have the tools to do it. So how do we do it? Well, instead of fixing delta and taking a filtration by the sublevel sets of the function, now we build a full, functional check or functional RIPS multifiltration. That is, we also take the scale parameter as one of our parameters for our filtration. So now we get a n+1 parameter filtration where the first parameter is the scale parameter. So here's a pictorial view of what's going on. So the first parameter is the scale parameter. This is your delta. And here you have Rn, where you have the codomain of the function. Okay. So the thing is now we have an estimator that is n+1 dimensional. So, I mean, parameterized by Rn+1. What should be the target? The target is parameterized by Rn. It's not parameterized by Rn+1. So what a natural idea to do is to take your target, put it on the vertical hyperplane, sitting at 0, and then extend it via isomorphisms, via identity maps, horizontally in the direction of the first axis. So basically, you're duplicating your targets in every vertical slice, and then you're connecting these slices with identity maps. And there's an operation from category theory that allows you to do it in a very natural way. It's called a left-hand extension. So you basically take the inclusion of Rn into Rn plus 1, that takes Rn and maps it to this vertical hyperplane at 0, and then you can extend to the right. You can extend along this your original module along this inclusion, and that gives you that exactly. So if you started with a module, in the case n equals 1, if you started with a module that had a barcode with a single bar like this, then when you can extend it, you get a rectangle, like a module that is supported on an interval module that is supported in a rectangle that goes to infinity to the right. Okay, and so now we're taking our new estimator is going to be the full, is going to be a smooth version of the full, functional RIPS multifiltration. So why is smoothing? Because for the same reason as before, we said, if you take a single delta, then you might not get a good estimator. So we took a pair of deltas, and now we're going to let delta, increase from 0 to plus infinity. It could be that a single delta at every value of delta is sufficient, but I don't know. So for now, we're taking a pair of values of delta for every we're taking delta and 2 delta for every value of delta, and we're letting delta run over R plus, and then of course the function parameter run through R. Okay, so we get what we call a multiplicative horizontal, because two smoothing of the function RIPS multifiltration. So smoothing because we're taking images of shifts of the module into itself, and it's a multiplicative because we're shifting by a multiplicative factor here, and it's horizontal because we're smoothing only along the first axis. That's where the terminology comes. And now we have this result that says that now we have, given this target and given this estimator, I can phrase an approximation result that says that, well, not only within each vertical slice, but within each vertical slab that goes from 2 epsilon to delta 0, or from 2 epsilon to, let's say, up to the convexity radius of x over 2, I get an interleaving, but an n plus 1 dimensional interleaving between the kind extension of my original target and my new estimator, which is n plus 1 parameters. Okay? So what this result means is it really looks like the previous result. It really is of the same type, but what it says is that if you apply the previous result to this new construction, what the previous result would tell you is that within this range, for any fixed value of delta there, if you restrict your estimator to the vertical slice at that delta, you would have a vertical interleaving, like an interleaving within that vertical hyperplane between your estimator and the ground truth. And now what this result says is that not only do you have these vertical interleavings at every step, at every value of delta within the range, but actually these interleaving actually commute with the interleaving maps, commute with the inclusion, with the structural maps of the modules horizontally. So you get a fully commutative diagram here, okay? And so this is very important because what it says is that if you have, like, let me show you an example. So if you have, we're going back to the example of the circle where we're taking homology in degree 1. And if you remember what happened in this case, if you take just the height function, what happens is in this case is that the ground truth is the 0 module up to level 1, where the sublevel set now includes the full circle. And so now I've got one generator in each one. And so my ground truth just has this barcode, a single bar that starts at 1 and that goes up to infinity. And now what the result says is that if I take the kind extension of this ground truth, I get this interval module. And now the result says that within this slab here, so going roughly from 2 epsilon to the convexity radius over 2, I've got a vertical interleaving of the two modules. Okay, so if I had this particular feature or generator in my ground truth, but if it was k persistent or epsilon persistent there, then it should continue to be epsilon persistent until at some point where if I drift by at most epsilon, it will continue to be persistent. It will not disappear. Okay, that's what it means, and it will generate something that is two-dimensional here, and that an invariant for two-parameter persistence models might be able to capture. So to be more specific, here we have a full interpretation of the result here. So what the result does, so what we have here is in yellow. What you can see in yellow is the persistent module that you would get with a function RIPS by filtration. Okay, so we're lucky. This example is so simple that all the modules are interval decomposable, so I can actually show you the module. So here we have a single interval in the function RIPS, and as you can see, as you move to the right, the approximation factor drifts. It increases. Okay, it increases linearly with the value of delta. And now, if I reparameterize this RIPS filtration by a factor of 2 in the delta parameter, I get this new interval module. And now our estimator is the image of the yellow module, of the morphism from the yellow module to the green module. And that gives you the blue module that is here. And as you can see, in the range that we talked about in the slab from 2 delta to half of the convexity radius, I get a very nice interleaving between our estimator and the ground truth. And of course, from this kind of interleaving, which is a vertical interleaving, you can deduce some interleavings, you can deduce some matchings for certain invariants. For instance, the multigradient numbers would be matched vertically within this range, and this is what I show in green. For the experts who know what the multigradient numbers are and what the stability for them is, I mean, this is an illustration of that stability, etc., etc. So here you see an illustration of the result. Here are some more examples. So the example with 3 annuli that I was showing up before. So this is an invariant that is called, it's not an invariant, let's call it a quote invariant unquote. This is called the MMA, and the MMA does show you three things. And in fact, these 3 things correspond to collating the bars from one vertical slice to the next. And this collating actually has a meaning, like it is possible because of this result that I just mentioned, the fact that in the slab you have a compatible vertical interleavings. And here's another example again, and I'll stop with this one. It shows another very simple example again. The points are sampled along a horseshoe, well, kind of distorted horseshoe, I should say. Okay, and I have 3 different horseshoes, and I'm treating them as intrinsic spaces. Okay, so each one of them is treated as an intrinsic space, so it's equipped with its own geodesic distance. So the distance between them is supposed to be infinite. Okay, I'm showing them in the plane, but they're supposed to be at infinite distance from one another. And along each one of them, I'm using the shortest path distance. Okay, so I have a space, an intrinsic space with 3 disconnected components. And and if you compute, and now the function, because this space is embedded, is now immersed into R2, I'm actually using the height function as my filter function. And here is on the right-hand side, the approximating persistence module that I get from my construction. Okay, so this persistence module exhibits, so that's the MMA of the persistence module, and it exhibits again 3 blocks. Each one of them corresponds to 1 horseshoe. I forgot to mention that here I'm taking homology in degree 1. Okay, so I'm looking at 1 cycle. And so this green block corresponds to this cycle that appears at a certain scale and then disappears, and then this yellow corresponds to this cycle here, and this red corresponds to this cycle which has not yet appeared in the picture, but that will appear here. And the funny thing is that we tailored the example so that one of the modules here actually ends exactly when the next one starts. Okay, and so why did we do that? Because now there is another example that you can cook up by taking this connected component and tweaking it a little bit, towards the edges. You can tweak it a bit in such a way that now you get a persistence module in your ground truth. Your estimator, now has this interval module, and it turns out that this interval module exactly has as support the union of the supports of these 3 modules. So if I didn't have the last result that I showed, I wouldn't be able to discriminate between this example and that example. My theory would not allow me to tell that it's normal that here I see 3 blocks and here I see only 1. If I were only able to say that what happens in each individual vertical slice then I would not be able to discriminate between these two examples. And this result really tells us that the modules that we get should be different in these two examples, and therefore here their invariants are actually different as well, and we can discriminate. And with this, I'll stop here.
Okay, thank you very much for the great talk. Before we go to questions, let's give a round of applause for the speaker. Okay, and with that, we are up to questions. So if you have a question, either just unmute yourselves and ask, or you can raise your hand or post a question into the chat and we'll read it out.
I'll start with a question on the slide, Steve. So the filtration you're using is this height filtration. And then
yes.
I was confused. You were saying that you were using the geodesic metric on the horseshoes. I mean, if you do that, why are they not just intervals?
Why are they not what? Sorry, just intervals?
Yeah, like if you put the geodesic metric on a horseshoe, isn't it indistinguishable from an interval? But then you hold these balls.
I see. It's a slightly distorted horseshoe. So then you see here, there's a one cycle that appears, and so individually, each persistence like each connected component here will give you a persistent module in one parameter that would have a single bar, and I guess that's what you meant by a single interval. And it has a single bar, and here you can see the bar corresponding, that goes to infinity, by the way. No, not to infinity, sorry, it goes from here up to this point. And it's the bar corresponding to this horseshoe. Then this is the bar, this would be the bar corresponding to this one. And of course, depending on the scale parameter that you're choosing, the bar corresponding to this horseshoe would, if you increase the scale, then the balls are bigger. So the bar actually is going to appear earlier because you're going to create the hole earlier.
I see.
Yeah, so but what I'm showing here is basically it's the approximation that I'm showing. I'm not showing the ground truth, and I'm showing the approximation in n plus 1 equals 2 parameters here.
Mm-hmm.
And in 2 parameters, what happens is that for the first connected component here, if you increase delta up to this point, then you see that the cycle never appears anymore. The one cycle doesn't have the time to appear; it gets filled in immediately. And same for this one. If you take a delta that is too big, then you won't have time in the sublevel sets. You won't have time to create this hole anymore. And same, of course, for this one when you reach that point. And the funny thing is that the way we set up the example is that when this closing effect appears on this example is exactly the value of delta at which we start seeing a cycle appear here. And that's what you see here. We see that we just barely close the one cycle, and here it barely appears.
Right. Very nice. Thank you.
Any more questions?
I'll ask another one. So this. Oh, go ahead, Honka.
I had a question about the choice of. So you choose a pair of ribs complexes. One is with delta, and the other one is with 2 delta. And I was wondering. Right. I mean, I was wondering about the 2 essentially in the 2 delta. Like I assumed it's because of the interleaving. But is there any, like, did you try to experiment with larger deltas? Or I guess smaller deltas you would run into trouble, but I don't know, let's say like choosing 3 delta, if it would change anything or if it's anyhow relevant.
Yeah, so the reason is technical. It comes from the fact that we want to interleave with a Chesh complex here. Because you see, what I showed you here, this progression at the beginning where I take the union of balls and then I take the Chesh complex and then I take the ribs complex. The reason why I did this is that behind the scenes, in order to prove that this image here is interleaved with the sublevel sets of the function at the homology level, I'm going to build a big diagram where I will see appear the sublevel sets of the function, the unions of balls, their nerves, so the Čech complexes, and then finally the Rips complexes. So I need an interleaving between Čech and Rips, and I need to actually be able to go from Čech to Rips to Čech to Rips to Čech. So that's why I need to go from Rips delta to Rips 2 delta in general. If you're in Euclidean space, you have actually a tighter interleaving between the Čech and the Rips, so you could take a smaller value of delta. And in experiments, we actually try to take even smaller values of delta. Actually, and it's interesting because, of course, at some point, things seem to collapse, although, again, they don't really collapse. That's the point. I don't have a counterexample that shows that really just a single Rips delta would completely fail. Like the example that I showed here, where is it? This one does not allow me to conclude. It just tells me, well, yeah, if you take the image, then you're smoother. But that's here, this does not contradict a potential result with a single Rips complex. Anyway, and then on the other hand, if you increase your 2 delta to a larger value, then you're going to get smoother and smoother. So actually, you can see this multiplicative factor as some kind of a, there's a bias variance trade-off here. So the larger this smoothing factor, the larger the bias is going to be in your estimator, but then the smaller the variance is going to be. And on the other hand, if you reduce the scaling this multiplicative factor, then you're going to get a better bias, a smaller bias, but you're going to get higher values. And this is illustrated by these curves.
Okay, thank you.
I had a question in the statistical setting. So you have this this extra log k, which is small. But if you had to guess, would you guess that for your estimator that log k could be removed, or?
So which k are you referring to here? Sorry. Is it in this slide or
yeah, exactly. So that extra log k factor.
Oh, the log k factor, yeah. Mm.
Is your guess that log k factor could be removed, or?
Yeah, my guess is that it should be the same thing as in the one parameter setting. So in the one parameter setting, I think they showed that the log k factor was actually needed. I think that's what they came up. I hope I'm getting it the right way. I hope it's not the other way around. I think it's this way. It's this way. So they showed in particular cases. So for instance, if you're looking at compact, maybe convex subset of Euclidean space, that was a different problem that they were looking at. They were not looking at estimating the persistent homology of an arbitrary function. They were looking at estimating the persistent homology of, say, the distance function to a compact set. And if that compact set turned out to be convex, I think they showed that in that setting they needed the log k factors were mandatory for any. They were there for any estimator.
I see.
If I remember correctly.
Thanks. Yep.
So I would expect that the same kind of thing would happen, at least in some special cases.
Right.
So I want to mention one thing, maybe if I have a second. So this open question, I think it could be of interest to you, Henry, particularly because you are among the people who have been studying a lot the behavior of the Rips complex, especially of point clouds or even of the space X itself. And you can really see this question as a kind of a filtered version of Hausmann's and Natcheff's theorems. So in Hausmann and Natcheff's theorems, you don't have a function. You just have either the space X itself or a finite sampling of that space. And you want to understand for which values of the Rips parameter, the Rips complex is going to be homotopy equivalent to the ground space. And now we want, what we're aiming for, what would be very nice would be a filtered version of that, where now you have a space together with a real value function or an Rn value function. And you want to know if there are Rips parameters, single Rips parameters that allow you to get a good approximation. I don't expect to be them to give you a module that would be isomorphic to the persistent homology of the ground function. Why? Just because we would probably have zero or close to zero control on what happens near the critical values. So the sublevel sets near the critical values might be extremely badly behaved. But at the very least, I'm hoping that there might be a result that says for fixed values of delta within a certain range, you should get an approximation within a certain interleaving error, which would be given by we would be driven by the curvature of the space, its convexity radius, and something like this. And probably something about the function itself, right? Also the regularity of the function would come into the picture. So you can really see this as a filtered version of Hausmann's problem.
Okay, so if there are no more questions, or at least recorded questions, thank you, Steve, again, and I'll stop the recording now.
Yeah, thank you, everyone. And a V2 of the paper is going to come out on the archive anytime soon. It's still not quite there. In V1, you only have the two main results, or let's say the first main result, essentially. But in V2, you will have the statistical analysis, you will have the robustness to noise, etc., and the algorithm and so on. So the V2 is going to be much richer. So please stay tuned. Don't download, well, you can download V1 if you want, but V2 will be much richer.